Bedrock rivers, such as the Temperance River along the north shore of Lake Superior in Minnesota, USA, as shown here, erode by sculpting the bedrock that forms their beds. And that might kind of seem like an obvious thing to say. Okay, so bedrock rivers erode by, or evolve by eroding bedrock? Sure. So the more complicated questions are, how fast do they do this? By what mechanisms do they do this? And kind of an idea to keep in the back of our minds, which is connecting this back to overall landscape evolution and questions about what processes carve channels and how are those linked to hill slopes and sediment supply, and kind of these broader scale questions we've been talking about. In this first image, though, I want you to pay attention to a few different features. One is on the left. I'm going to move my mouse over here, right there, where my mouse pointer is. So that feature is called a pothole. And that is formed by rapid, swirling, turbulent water flowing over this portion of the bedrock surface that has picked up a class that's grinding and drilling down through the bottom of that, the vortex that would be formed in that when the water is very high. Or, potentially, if no modern flood goes that high, it would have been formed at some point in the past. And these features are really common from large-scale outburst floods, as well as events such as, deglacial outburst floods, so floods that happen from the glaciers, basically big flow events. The other thing to keep in mind is that some of these rocks have these sort of chips on the side, like that, and it looks like there's been some breaking along some pre-existing fractures. And as a matter of fact, if you use a bit of imagination, you can kind of trace the outline of the tops of basalt columns around here. So these hexagonal cooling structures that form in basalts. And so it might look like these rocks are breaking along those pre-existing fractures. So think about that as well. And the third thing just to keep in mind, as we consider the different discharges that might go down this river, note this tree trunk right here that is spanning the river gorge at some distance above the water. So know that from this, you know that there must be some higher flows that occur than the one that I photographed here back in 2012. And so here's another view of the Cascade River, or of the Cascade River, right, rather than Temperance River. And this is of a small waterfall. And a waterfall like this isn't a feature that you would expect to see on an alluvial river because the sediment would move and the portion upstream of the waterfall, so sort of on the left-hand side, would erode, and that material would be deposited down here to create a smooth, continuous bed. And so that's another important thing, is that waterfalls such as this really only form in detachment-limited settings, often in bedrock channels. And again, as we look across, we can see some clear signs of this kind of blocky erosion. We also see that there is at some point a block fall, so a mass wasting event that dropped a block into the river right here. And then over here, we can see again another one of these blocky rock faces. So we've talked a little bit about these rivers now, and so what are the conditions required to erode to bedrock and to erode through bedrock? Well, first, we need to make sure that sediment inputs are less than the sediment outputs. If the sediment inputs are greater than or equal to the sediment outputs, then that will lead to a situation in which the bed is covered and the river cannot reach the bed. And so this is actually a little bit strangely worded, so I apologize. What I really mean here is that the sediment inputs are less than the sediment outputs for a long enough time to erode through any deposits and reach the bed. And so then what would happen after that is the potential to remove sediment from this river reach would exceed the amount of supply entering the reach. And so the bed would always remain accessible because the flow would always be able to scour away that sediment. And this is one of the reasons why some rivers can transition from being a transport-limited, more alluvial system to being a detachment-limited, more bedrock system, because they can have some periods of sediment cover or some zones of sediment cover, And either in space or time, those zones of sediment cover can move, for example, as a waterfall migrates upstream, or those zones can gain and lose sediment cover, for example, over the course of climatic changes that affect how fast hill slopes weather and how much coarse sediment arrives from the hill slopes at the channel. And so if there's more rapid mass wasting, then there's more material from the hill slopes arriving at the channel, and then there can be more sediment cover that then leads to a more alluvial style bed. Eroding bedrock, however, does require some sediment to be present to either help abrade the bedrock or to help act as a wedge, which is, in a way, I'll show this to you, a one-way valve that helps to push blocks in the river towards failure. So, bedrock river formation occurs and evolution occurs via a couple major mechanisms that I just mentioned, as well as a third one that I haven't. So the first one is abrasion, and that's removal of small pieces of rock bit by impacts from particles. And so this figure at top right shows that. And so if you imagine the path of a particle, it might start moving up like this, and it might impact and chip at this bed a little bit. And then it might reach a zone where there's a sharper face and the flow starts to separate. And by that we mean that this top part of the flow moves continuously over this in one single stream, but over here there's some eddying and some mixing. And this, you can think about this as just a big roughness element, and this is affecting the very bottom of the boundary layer of the fluid flow. So if we're kind of bringing our brains back into turbulence mode. And so then this turbulent flow will carry rocks that can attack this backside of the obstacle, or the lee side of the obstacle as we call it, and erode that as well. A second mechanism is through quarrying of blocks. So a lot of bedrock, when it reaches the surface, already has some fractures in it. And those fractures could be from cooling, like in the case of those basalt columns, and it could also be from what we call, the tectonic rock crusher. So if there are rocks that are folded and faulted as they're being brought towards the surface, those stresses will impart strains. And as the rocks move up towards the surface from the ductile regime, farther below, into the brittle regime near the surface. And so for those of you who might not have had as much background in geology, rocks that are buried deeply beneath the surface, but still on the Earth's crust, can actually deform essentially ductily, so by folding instead of by breaking and faulting. So these rocks that are at the surface then, as they cross that ductile to brittle transition, can then start to accumulate fractures. When a rock that has very, very few fractures arrives at the surface, it's extremely difficult to erode. And so a classic example of this is El Capitan at Yosemite National Park. So this big, or like Half Dome, these big, single, very, very solid hunks of rock. On the other hand, most rock comes with significant fractures, and these fractures help it to fall apart, unlike something like Half Dome. So this bottom figure shows, that you could have a rock that impacts this, that maybe creates a few fractures, and maybe also nudges this block forward. There's also a shear stress imparted by the flow pulling this block forward. And what you can imagine, if you think about the fact that turbulence leads to fluctuations in flow velocities, that the shear stress isn't constant. It's actually increasing and decreasing with the motion of eddies past this block. And so if it speeds up just a little bit and slows down a little bit, it might not move a whole lot. But let's imagine it speeds up, and as it does so, it opens a teeny tiny gap that you might be able to put a piece of sand or maybe a tiny piece of gravel into. Then when it tries to snap back, that rock will be in place, and that will prop this crack open. And over time, the actions of sliding back and forth and then having sediment fallen back here will gradually shuffle this block towards the edge where it eventually falls off. And if it falls off and doesn't break, well, then it's just a gigantic piece of sediment, a big boulder sitting in the channel. If it falls off and then it breaks, it might break into some smaller pieces that the channel is then able to transport, or the flow in the channel is able to transport much more easily. The third one, which isn't pictured here, and I'll talk about in the last couple slides, is detached jets. And so these are waterfalls. These, as I mentioned, only really occur in these detachment-limited bedrock systems. And in these, erosion still happens via one of the two above mechanisms, but I think it's important to mention that just because waterfalls are just these big charismatic features, and they also are where there's a significant amount of bedrock erosion focused. So, first off, abrasion. So on the left, you can see a measuring tape next to some flute marks. So these are these abraded chips, and those are all on the lee side of the flow. So in that figure, the flow is moving from left to right. And this, again, is linked with that same picture I showed you before from the Anderson textbook that is illustrating the damage in these pits due to bedload impacts. And as another example, so of course for textbooks, and especially with someone like Bob Anderson, who's a photographer as well as a geomorphologist, you'll get this sort of ideal picture. But I wanted to show you kind of a more just everyday picture, and which I took just while walking along on the Superior hiking trail, and I found took a couple minutes just to find a decent looking abraded rock, but nothing super special. And so again, we're looking upstream to downstream, and this is the smooth side, and you can see these fractures right here that have been taken advantage of, and there's some scouring back behind that. So this is along the Cascade River when I took a 2.5 day fun little jaunt up there on the Superior hiking trail by myself. Another example of abrasion, you can see this really smooth bedrock surface, and this looks like a limestone. In fact, I could probably name the unit, but I'm not going to stress myself that far. But you can see these small pieces of gravel in it. And so those hunks of gravel are moving across the surface even with a small amount of flow. And by the way, this is a tributary to the Grand Canyon in Arizona. And seeing these sorts of streams flow is a pretty special occasion because they don't always do so. This chocolatey brown color is from a large amount of suspended sediment, so think silt and clay that's being held by the flow. And this gravel is being moved along and is bouncing along and hitting the bed. And it's not clear whether this little tiny flow is really enough to do much work on the bed to really evolve this landscape and to cause the river to erode. But you can imagine that some larger class might be able to. So here's a picture of a larger landscape that's shaped by abrasion. So the main thing to see is just the fact that there are all these really, really smooth features. Smooth canyon down there, smooth valley walls, everything is just being gradually abraded away. And you can think of abrasion also just like sand blasting, except sometimes it's also gravel blasting, which would be really harsh if you use that in any kind of industrial application. So abrasion requires tools, right? It requires rocks, especially hard rocks. And if there are more rocks to abrade, you might think that the abrasion might happen faster, and that's true to a point. And so this curve over here, and this is a figure modified from a figure originally by Leonard Sklar. So on the lower left-hand side of this curve, there is no erosion at all happening. And at the lower right-hand side of the curve, we're also approaching no erosion at all happening. And this is the amount of sediment mass that was put into this barrel for this experiment. And so let me explain this. So here's a barrel that in which sediment has tumbled. So the barrel is rolled around, and there is a plate of bedrock, and that plate is being eroded. And the erosion rate is calculated, and then that's compared with the amount of sediment mass that's placed into the barrel itself. So on the y-axis is this erosion rate, and on the x-axis is the mass of sediment. And so, all right, so now let's get back to where we were. So initially you'd think that, well, or at least I would think that if there's more sediment, there are more impacts with the bed and there's more erosion. And that's true. It's true to a point, and actually the idea about more impacts with the bed is true in general. Because if too much sediment is added, then the bed starts to become covered. And so these rocks are running into each other instead of hitting the bed. And eventually there's so much sediment on the bed that it's just completely blanketed. And yeah, the sediment might be rolling along the bed, but it's not able to, get up into the flow and then impact the bed in a big way that causes it to erode. And so again, on the left-hand side over here, we have no erosion. That goes up to a maximum at some intermediate amount of sediment. And then down here goes back to another minimum where there's no erosion once the entire bed is covered in sediment. And so that's this idea where this would be over here on the far left. This would just be bedrock with clear water running over it. Nothing would happen. And on the lower right, we have, essentially a condition in which we're approaching an alluvial river. And this is telling us, similarly to what I was mentioning before, that the alluvial river will have to erode down to the bed before it can start really actively working on the bedrock. And that just sort of makes common sense. And in this experiment, 3 different kinds of rock were used, and these are the tensile strengths. So sigma sub t is the tensile strength, and you can think of that as a stress that's related to the cohesion of that material. And mudstone is the weakest, and so you can see the mudstones are generally plotting over in here, right? And you can see that there are limestones that are plotting up here, and the andesite, which is stronger, that's plotting up here. And it seems that they're actually all plotting pretty well together on this curve, even though there's a strong difference in tensile strength. And so the question is really one that's much more of the sediment impacting the sediment dynamics than it is about the strength of the materials. The second major mechanism is quarrying. So while with abrasion you have to remove all sorts of material one chip after another, quarrying is a mechanism that allows large blocks to be moved one at a time. And so, but one at a time in mass, right? So these are big pieces, not little tiny pieces. And so in this figure from the article by Whipple et al. 2000 that I've just borrowed this from right here, we have this block that's clearly been moved and seems like it's very, very close to dropping in the water. And as a matter of fact, one of my former master's students, Shane Loeffler, used to do a bunch of cliff jumping around Duluth and had some of his favorite rocks that he would jump off that were later quarried in floods and moved downstream. And so his spots were changed by bedrock erosion. On the right-hand side here, this is again the Cascade River in northern Minnesota. You might notice that I take a number of lecture photos during fun trips, and I like to do that. It just kind of feels like if I'm out there, why not? So over here we have all of these fractures, and you can see this hackly surface. And so again, it's not so perfect for a picture as these nice rectangular blocks, but something like this that's very hackly will indicate that there's been significant quarrying. And these rounded edges here indicate that there's been a bit of abrasion as well. Typically, however, quarrying is a more effective mechanism because it's able to move larger chunks at once. And quarrying can be particularly effective at waterfalls. And so this is a tributary to Marble Canyon in Arizona. And so we have this head wall right here for the waterfall. You can see that there's been some abrasion at the surface, but mostly we have these larger blocks toppling down here, and there are a couple eroded blocks there and there. And then those blocks are washed away in larger floods that then move them downstream, break them down, and turn them into sediment that can be more easily transported. Right here in the middle, where most of the flow concentrates, is something that we call a plunge pool. And that's formed by rocks and water moving directly off the center of the channel, falling in here, and then mixing up and stirring and bouncing around. And so this kind of erosion is also abrasion, but it's something that happens with detached jets, and we'll talk about that more in a bit. So I showed you this picture before and described it in some detail, but just very quickly again, remember we could have rocks hitting this and fracturing it, or the rock impacts actually shuffling the blocks along, or turbulence in the water moving that material. And then as these blocks shake back and forth, these clasts wedge themselves in behind these blocks, and that can lead to crack growth and eventually shuffle the blocks along here. And as a field photo that I took, again, in a tributary to Grand Canyon, we can see a couple examples. One of them is right here at the top, really obvious, right? This is propping this block open. And you can also see a bit of chipping here at the surface, so that's sort of like this micro-scale quarrying. And then below it, look at this. So this block, this little piece of rock, I was trying to get a good picture, it was hard, is basically a perfect triangle. And then it's shattered such that there's a fracture plane moving directly downstream. And for those of you who might have taken a solid mechanics class, or perhaps structural geology, you might notice that this is a really like perfect tensile fracture. And so what this is that the rock came in here in this direction and here in this direction, but mostly just the downstream side came back in. This poor pointed rock was caught between them in the wrong position, and it smashed it. And because the compression was coming between in the directions in the kind of top and bottom of this photo, so this is downstream, so the downstream to upstream side, and there's a free surface to the left and the right of the rock, its preferential way to fracture was actually just to pop apart directly in the middle in a way that's perpendicular to the two sides that are crashing into it, and just pop and snap apart like that, open to the free surfaces. And so that's a classic mode of tensile failure. And what that indicates to me is that that rock fell in when these little jaws were a little bit more open, and then was smashed when this rock came back here. And so I found this, when I saw this in the field, it was shortly after I had read about some of these hypotheses. And so I thought that that was pretty good proof of the rock wedging or rock hydraulic wedging hypothesis. And again, here's a Grand Canyon tributary showing that both abrasion and quarrying are present. So there's quarrying of these larger units here. You can see these bigger pieces that are broken off, but then abrasion kind of ornamenting that. And that's quite common, is that there'll be some ornamentation, by which I mean some small-scale, local-scale erosion by abrasion. But typically, if there's any fractures of any appreciable density, if there are any fractures of any appreciable density, and by density I mean how many fractures you have per unit distance downstream across the channel, or just walking across the bedrock, do you see frequent fractures? Then there will be significant quarrying. And I just realized that my favorite snowflake water bottle, which I lost at an Ultimate Frisbee game back in 2012, is over here. I miss that thing. So, in addition to thinking about bedrock and alluvial rivers, sorry, why did I say that? In addition to thinking about abrasion and quarrying, we can also think about processes that occur with detached jets. As you can see in the lower left here, those detached jets, which are waterfalls, will often form these great abrasion-related features. Detached jet is just the hydraulic term to describe them. Waterfall is more the geographic term to say what that is. And so in these cases, water detaches from that surface, falls, enters a plunge pool, and then carves holes into the rock beneath it. And so that's like this case as well. And so these holes can vertically drill down into the landscape, and that's one way of evolving and eroding this profile through the river. And they can also retreat laterally by eroding backwards beneath the cap rock that the waterfall is flowing over and causing that to eventually collapse. And so this example here is quite common. It occurred at places like St. Anthony Falls here in Minneapolis or in Niagara Falls. This example of vertical drilling occurs in this lower left photo as well as the upper left photo over here. And one cool thing to see also is that in C down here, we have this sort of vertical drilling right here going on, and then we have multiple abandoned plunge pools in this river gorge on the approach to this waterfall. So, where does each of these erosional mechanisms dominate? And I think I've been kind of trying to hammer this home. So abrasion can occur in massive, that is, unjointed, solid bedrock. It's often slower, but the only way to erode this sort of more perfect, unfractured rock. Quarrying, works for bedrock with pre-existing weaknesses, that is fractures. And as you can imagine, if the fractures are more closely spaced, it will be easier to quarry blocks, right? It's a lot easier to lift up and move a block that's 30 centimeters by 30 centimeters, so a foot by a foot, than it is to move a block that is 1 meter by 1 meter or 5 meters by 5 meters. And once these blocks start getting really, really huge, then we move back to just being able to move material and erode bedrock via abrasion. But if quarrying is possible, it will cause much more rapid evolution of the bedrock valley. And the third option is through a detached jet. And that's sort of, more of a flow description than an erosional mechanism. But because so many of our examples are just from continuous flow inside the river, I want to remind us that waterfalls can be important in rivers as well. There can be very important agents of geomorphic evolution. And you can even imagine that there is a transport-limited alluvial river that exists above and below the waterfall, and yet there's still bedrock erosion occurring at the waterfall in this small localized steep zone where no sediment can collect. And so with that, waterfalls are quite important. I believe that is it, yes. So those are our major erosional mechanisms and possibilities for bedrock rivers. And from here, we'll start to think a little bit more about flow through rivers and how that flow links to rates of erosion and how we can start to predict landscape evolution.